In a previous video, we introduced randomized decision rules, which after we observe the sample data, gives us a probability distribution on the action space. We also talked about various other possibilities like how to turn a regular non-randomized decision rule into a randomized decision rule, and also that if you have a decision rule with no data, then that's referred to as a randomized action. We also looked at this example where you and your opponent each have a coin and you decide whether to flip it to heads or tails, but neither person knows what the other person's coin shows, right? And then both are revealed, and then if they both match, you win $1, and then if they don't match, your opponent wins $1. And so we said that you choose are the actions. A1 is you choose heads, A2 is you choose tails, and then the unknown, the parameters. Theta 1 means your opponent chose heads, and then theta 2 means your opponent chose tails. And so there are 4 possibilities. We looked at the loss matrix and so forth. We also talked about a strategy for choosing our actions. So a strategy for you to choose your actions. So really the only option here to do this in a randomized way is for some little p, some probability, you choose A1, and then with the probability 1 minus little p, you choose A2. So you choose heads with probability, for example, 1/3, and you choose tails with probability 2/3. Okay, and then we also mentioned a way to denote that. So we won't go through all that again. But we did not talk about the loss function for a randomized decision rule. So remember, we know what loss functions are, and the randomized decision rule gives us a probability distribution over the action space. So we can take the expected value of this loss function with respect to the action. For the randomized decision rule no longer is in terms of A because we've quote unquote integrated it out. So at this point, this loss function would depend on the value of little x, that still may hang around somewhere, and then also the value of theta. The risk of this randomized decision rule is what we get if we take one more expectation, and that is we take the expectation with respect to the data. So if we take the loss function of the randomized decision rule, which again is in terms of x and theta, and we take the expected value of that with respect to our data, with respect to our random sample, then we'll get the risk function, and now we have something that's only in terms of theta. And as you see there in no data problems, then the risk and the loss are the same. All right, so let's apply this to our example. So we'll continue with example 8, where you and your opponent are playing the game. And so let's calculate the risk using the randomized decision rule that we chose. And since this is a no data problem, remember that the risk and the loss are the same. And so the loss of the randomized decision rule is equal to the expected value of the loss function, where we take the expectation over the action space, over the A's. And so then at this point, since this is a no data problem, we clearly have a function that only depends on theta, which is what we think about when we talk about risk functions, right? Every time we've seen a risk function, it's been just a function of theta. Okay, so now let's think about how we're going to evaluate this expectation. Well, remember we had our loss matrix before. So just to review that, just to recall, there's our loss matrix. Okay, and so since we're taking the expectation with respect to the actions, we only have two actions, and the probability, the PMF essentially is what this is, since we just have the A1 and A2. So this delta star of A1 is the probability that we choose A1, so that's little p. And then the loss of theta comma A1, well, that's going to depend on what theta is, so we'll get to that in a second. And so then plus the probability that we choose A2 times the loss that's associated with A2. So again, delta star at A1 is little p, and delta star at A2 is 1 minus p. And then now we've got to deal with each of those losses. And as we know, the loss will depend on what the opponent did. So in the first case, let's assume that the opponent chose heads. So if they chose heads, then that means in the case where the opponent chose heads and you did also, then you win. Remember, you are the winner if the two coins match. And so that is a loss of -1. And then if the opponent chose heads but you chose tails, then the opponent wins and you actually lose, and that's why we have a +1 there, because you actually had a loss. And then similarly, you can go through the cases if the opponent chose tails, where theta is theta2. In both cases, what you'll see is a line. So if we look at the first one, we have a line that decreases with p. And so if p is 0, then the risk would be 1. And if p is 1, the risk would be -1. And then in the second case, if the opponent chooses tails, then the risk is a linear function of p that increases. And if p is 0, then the loss is -1. And if p is 1, the loss is 1. So how about we just try to aim for a loss of 0 in all cases? What will that require? And what does your intuition tell you that would require? And remember, little p is the probability that you choose heads. And it turns out if you set both of those expressions equal to 0, you get p equal to 1/2. So the only way to ensure that you have 0 loss in any situation is for p to equal 1/2.